All right, if just as a kind of reminder, we've done this in very, not too long ago, but integrating with respect to y. Of course, actually integrating this, not a big deal, because all you have to do is the antiderivative, 1/2 y squared plus 5y from 0 to 4, so that's 1/2 times 16, 4 squared, plus 5 times 4 is 20, and then plug in the 0, of course, those are zeros, so it's half of 16, 8, plus 20 is 28. Okay, well, that part of it's not hard, but what we need to understand is what we're doing there, the graphical interpretation of that, because that's going to come out a little bit as we go along through the rest of the term here. What does this mean? Well, we're integrating with respect to y, and so first of all, this is our defining expression or whatever, but what's the actual function that I'm graphing? Well, this is, since I'm integrating with respect to y, this is a function of y, which means this expression gives me the x value. Because when I do functions of y, that gives me x values. So the equation here is not y equals y plus 5, it's x equals y plus 5. So that's how it works if I'm integrating with respect to y. This is an x equals equation, or function of y, if you will. All right, well, that's not so bad. That's still just a line. However you need to graph it, let's see, the x-intercept would be positive 5, the y-intercept would be negative 5, that's one way you can do it, or y equals mx plus b if you want to do it that way. So it's this line. But what's that 28 refer to? It's an area, but since I'm integrating with respect to y, this is an area between the curve and the y-axis. And what area between curve and y-axis am I talking about? Well, it's between these y values, right? Since I'm integrating with respect to y, these are y values. So I'm going from y equals 0 to y equals 4. So y equals 0 to y equals 4. It's that area between the curve and the x-axis. Y-axis. All right. Now, the other thing that, this one was already spelled out that I was integrating with respect to y. But the other thing to mention is when I integrate with respect to y, the typical rectangle, if I did an approximation type thing, that's what it's talking about, the typical rectangle. What does a typical rectangle here look like? Well, again, it's from the curve to the y-axis. That's the typical rectangle. So, I mean, you draw it whatever width you want to, but wider and narrow than that. But that typical rectangle looks like this. Now, the significance of that, or what I view as the significance of that, one of the key parts to that is to notice that the typical rectangle when I integrate with respect to y is sideways, left, horizontal. When I integrate with respect to y, when I integrate with respect to x, the typical rectangle is vertical. Okay? So when I integrate, when the typical rectangle is horizontal, that means integrate with respect to y. Vertical means integrate with respect to x. Because sometimes we won't know, well, do I integrate with respect to y or with respect to x? Well, if the typical rectangle is horizontal, it's integrated with respect to y. if the typical rectangle is vertical, you integrate with respect to x. So I wanted to review that, because that will come up in the near future. Now the other thing, let me mention here, this one isn't an integral, just a graphing thing. So if I'm graphing an x equals y squared minus 5, let's say. We haven't graphed many of those. I don't know that we've graphed any of those. What does that graph look like? Well, let's think the other reverse here, inverse if you will. If it was y equals x squared minus 5, that's an x squared graph shifted down 5. Well, this is the inverse of that. So what do you think that is? Well, that's a parabola that opens up down 5. This is x equals y squared, and so that switches it around and makes it a sideways parabola. And the minus 5 here means I'm going to shift it, and it probably goes opposite what you might think. The minus 5 is actually going to take it to the right 5. Yeah, so instead of up or down parabola, it's a sideways parabola if it's x equals y squared. And then the minus 5 shifts it 5 units right. It goes opposite what you might think there. Oh, sorry. Wait. No, doesn't work. 5 units left. Not messed up there. Yeah, this one goes down, so this one goes left. So it's like this. And you get some other points. But I did want to mention, just give you an example of one of those, because I think one of those just happens to come up real quick here. But yeah, that's a shift down, so this is a shift left for the sideways. Plus would make it go right. Okay. Anyway, let's talk about this one. Let's say I had two functions that were functions of y. So I've got x is a function of y here, and I'm just going to make up kind of a graph, but it's x is a function of y. And then I have a second function, x is a function, another function of y, I call it g of y. And what I want to do is find the area here from C to D. I want to find that area between the two curves. How do I do that? Well, it's an area between curves. And so much like when I have functions of y, functions of x, I'm going to subtract the two functions. I'm going to subtract one from the other. Now, guess which way it is? Well, when they're functions of y, you do the right one minus the left one. So it's g of y. So I do the integral of the two subtracted. I do the right g of y minus the left one f of y. Right minus left. If we're talking about functions of y. Now, the other thing is, it probably may be obvious, but here, do I integrate with respect to y or with respect to x? Well, if you look at it, the typical rectangle, if you think about it, I definitely would want to do typical rectangles like this. Because then I'm just going from this one to this one. You see what I'm saying? If I did vertical rectangles, all right, so I do a vertical rectangle here. Well, I'm going from this line to this line, but when I'm over here, I'm going from here up to that line. So it switches, upper minus lower, you see. I don't want to do that because that's way too complicated. I just want to go typical rectangles this way. So that's integrating with respect to y. And maybe that's what I should have started with. But that's the kind of the purpose of the typical rectangle, because that kind of decides which way you want to integrate with respect to y or with respect to x. So in this case it is with respect to y, and so that's why I do the right minus the left. And then of course I do the c to d, those are the y values. Yeah. So if I've got that set up, that's the way to go. All right? Okay. So let's do one. Maybe that comes up. All right. Find the area enclosed by x equals y plus 1 and y squared equals 2x plus 6. Okay, let's draw the graphs here. This is just a line. You do it however you want. I look at that, I do the intercepts, but do however you want to graph. Do it y equals mx plus b. Be something like this. However you want to graph it. Points, table, I don't care. But I'm going to leave it in that form just so you can a second. I could move it around some, but yeah, the other thing, then the other equation, y squared equals 2x plus 6. And that was the reason I mentioned the example I did just a second ago, is because that, well, I've got the x is not squared, the y is squared. That's a sideways parabola. Now in a sideways parabola, usually you want it in x equals form. And so let's move this around, make this x equals form. So I'd subtract 6, then divide by 2, everything. So I'd have y squared over 2 minus 3 equals x. Yeah, so that one's more like we graphed just a second ago, right? It's a y squared graph, if you will, and then minus 3 means that's going to shift it 3 units back here. So that's going to be my vertex. And, you know, if you wanted a little table here to help you kind of graph it. I think most of them you can get a couple of points, and well, actually, since I've got x equals in terms of y, I probably want to do my y as -1 to positive, -1, 0, positive 1. Because then the x would be -1 squared over 2 minus 3, but y is -1. So that'd be a half minus 3, is that -2.5 for the x. Y is 0, so that'd be 0 squared over 2 minus 3, so that's -3. And then y is 1, so that'd be 1 squared over 2 minus 3. just get a couple of points. Negative 2.5, negative 1, negative 3, 0, negative 2.5, 1. Just to kind of give you an idea of what it looks like. Okay. Now, question is then, how am I going to find that area between enclosed? Well, the first thing to establish here is I'm going to want to integrate this with respect to y, aren't I? Because look at the typical rectangle here that I want to use. The typical rectangle that I want to use is like this. Why would I want to do the typical rectangles like that? If I do the typical rectangles up and down, yeah, I'm going from here to there at this part, but then the typical rectangle over here is going from here to here. So the upper one is this, the lower one, it's the same function. I don't want to deal with that. You see what I'm saying? So I definitely want to integrate this way, rectangles like this, which is integrated with respect to y. Right minus left. Good with that? So do right minus left, and I'm integrating with respect to y. So that's the typical rectangle. That's important that you understand that, so if you have a question about that, just let me know. With me there? Okay. Now the one on the right, so I'm integrating with respect to y, so I need x equals equations, which I've got this one already. That one's on the right. The line one is on the right, so it's this one. So the right would be y plus 1, minus the left. Well, that's another reason for getting it in this form, because here's the one on the left. I mean, it's originally started here, but for this, it needs to be this. X equals this. So this is my other part of it. Y squared over 2 minus 2. All right? Now all that's left is those upper and lower limits, which in this case, yeah, still call them upper and lower. What are they? Well, it's where they intersect. It's where this and this, so I would need, call it C and D. How would I get those? Same way I get them elsewhere. I just set the two x equals equations equal to one another. So y plus 1 equals y squared over 2 minus 3. Solve that. I'd probably multiply everything by 2. Make it 2y plus 2 equals, now 2 times that, the 2's will cancel, so it'll just be y squared. 2 times that will be 6. Makes it a little bit easier to handle. So let's subtract 2y and subtract 2, get this side to be 0. So it's y squared minus 2y, and then the minus 6 minus 2 is minus 8. That's going to work out nicely. Minus 4 and plus 2. So that would be, set that equals 0, that's y equals 4. Set that equals 0, that's y equals negative 2. So the y values goes from negative 2 to positive 4. You with that? Is that all right? Then we just have to do our integral. See, that'll be y plus 1, and that'll be minus y squared over 2 plus 3. And so if we go ahead and simplify, put them in order, don't have to, but we can add the 1 and 3 there. Something like that. Yeah, it's just a nice little antiderivative. It would be negative 1/2. Then the antiderivative there would be 1/3 y cubed The antiderivative there is 1/2 y squared. And the antiderivative there is 4y. And do that from -4 to 2. Sorry. -2 to 4. So that's -1/6 times. So the y, first of all, is 4, so that'd be 4 cubed, that's 64. Y squared would be 16. Y is 4. It's half of 16. This will be 4 times 4, so that's 16. Plug in the -2, so we have -1/6 times -2 cubed is -8. 1/2 -2 squared is +4. And then 4 times -2 is -8. Leave all that out. And I get, if you get, same thing. $18. All those fractions, it still comes out to be 18. Is that okay?